Hello there. Hope you guys are doing well this week. I just wanted to go over a couple of things very quickly related to the set theory from this week's assignment. If I start here from the assignment directions from this week's assignment, I'm sure you guys have already read through this all and seen that I left two pieces of notes here. I'm going to open up those other pages of notes and just highlight a couple of things that I want to make sure you guys are okay with. On the first set of notes here, I have some definitions about what a set is what a subset is. And as I go through here, I start doing an example where I say that two sets are equal if one is a subset of the other, and both ways. A is a subset of B and B is a subset of A. In this example, I use this to show that A and B are equal. For example, first I show that A is a subset of B by letting X be an element of set A. Once I do that, I know X is 2P because that was the definition of set A. Then I might notice that if I pick a larger value of P, I can rewrite the X as being 2 times P minus P plus 1 minus 2. I can rewrite it in the form of B. So now I know that since whenever X is in A, X is also in B, so A is a subset of B. Likewise, I can do the same thing by letting X start with an element of B, and just doing the same trick backwards, I can demonstrate that X also happens to be in A, and B is a subset of A. Here's the important part. What I really wanted you guys to see out of this is not just that you can show two sets equal to each other this way, but also the way that you can show subsets using an elemental argument. We started by assuming X is a generic element of A, and then we showed it is also some element of B, and that's why A is a subset of B. That kind of logic is very important and something that I wanted you guys to see. If I continue through, I got a few definitions here. I think you guys have done Venn diagrams before. So now I'm going to move over to the second set of notes. This has some theorems of inclusion. It starts talking about how intersections and unions work. We have some properties of sets. And then what I really wanted you guys to notice was right here, where it talks about prove the union of A and B minus C is A minus C unioned with B minus C. Kind of like in the first unit this semester, we discussed algebraic proofs of logical statements. Here we can use a lot of the same rules with set statements. So here, based on the definition of a set difference, which was right above this in the notes, I know that A union B minus C is the intersection of the union and the complement of C. Then, using that, we can distribute. You see those notes a little bit further above here. We can distribute and have the complement of C intersected with A, unioned with the complement of C intersected with B. This is distributing an intersection over a union. It is very, very similar to distributing an and statement across an or statement when we were doing logic. As a matter of fact, in a lot of ways, the set theory and logic stuff is very, very similar. Once I've distributed, the intersection of A with C complement is A minus C. The intersection of B with C complement is B minus C. That's what I really wanted what we wanted to get to. So I wanted you guys to become familiar again with using this kind of algebraic argument to prove set statements, much the same way we did with logic at the very beginning of the semester. If I keep scrolling down through the notes, they talk about the empty set or the universal set. We talk about partitioning things. And then I wanted to briefly mention the power set. The power set of A is the set of all subsets of A. So, for example, if A was the alphabet, we would have in the power set of A a set with one element for every letter, and then we would have all of the possible two-letter combinations of the alphabet, and then a set with all possible three-letter combinations, and we would have different sets for everything that could have been made up of part of the alphabet. That's a lot of sets. So I do want you guys to notice right here how many elements are in a power set of A. 2 to the nth if there are n elements. So how many different things would be in the power set of the alphabet? 2 to the 26th power, which is huge. Why is this? We can actually make a counting argument. For the first element of the set, when we try to build a subset, we can either include it or not. 2 options. And then if we move to the next element, we can either include it or not. 2 options. So continuing that, we have 2 options for every element of the set, and that ends up meaning we get 2 to the 26th total elements. I hope that was helpful. I was just trying to quickly go over a couple of key ideas. If you have any other questions, I know I keep putting this on all of the materials, but please email me. Please post to the discussion board on Canvas, and we'll try to make sure that we have everything that we need. Thank you and good luck.